everybody. I think we can start. So today we have two speakers, two slots. One is from University of Bolzano, Andrea is here, and the other one is from, sorry, I mixed up, sorry. And yeah, I think we can start with Andrea. And Andrea is a Andrea is a doctoral student at Free University of Bolzano, and he's doing he's working on smart mobile factory concept, which he will present shortly together with Dani. So I think I can give word to you, Andrea. You can start.
Then welcome everyone to today's seminar. We're going to be presenting a very interesting talk about designing a smart mobile factory for sustainable Hyperloop constructions, specifically talking about enhancing the efficiency and environmental sustainability in linear infrastructure projects. So the title may hear a bit of complex, but it's not. So we will break down the title in several blocks so it's clear for everyone. To start with, here at EuroTube, as you may know, we are focusing on realizing the Hyperloop. So for that, we are not only providing open accessible research infrastructures, but we are also looking into how to integrate Hyperloop in a European network. This European network is also comprising Switzerland, and as you can see in the right image, there is a preliminary selection done between Zurich, Lausanne, Geneva, which are connecting lines, and a bit of an idea of how such a infrastructure could be looking like can be seen in the image of the bottom left. So based on our first studies, we estimate that every 3 to 10 kilometers we would have a Hyperloop hub, which is enabling people to switch to get it outside or inside the pod whenever needed. So now the question, when building this infrastructure, assuming that concrete is the primary material, how do we do it in an efficient and sustainable way such that we are not also, let's say, polluting that much, we're not leaving a CO2 footprint once we're building the infrastructure. For this, together with the University of Bolzano, ETH Zurich, and TU Delft, EuroTube has launched since 2022 a research project which is on how to realize so-called mobile factories, which are also smart because in a way there is a digital twin behind, such that we are also knowing specifically where along this route it makes sense to build this factory, such that we are then able to come in with the material, assemble the pipe work, and then installing it on site. So now I leave the word to Andrea, who is going to be presenting more specifically how this mobile factory is looking like and how is it realized.
Thank you, Daniel. So today I will present some of the result of this project that is called the Smart Mobile Factories for Infrastructure Project. And it is a collaboration between ETH Zurich, EuroTube, UniBZ, that is University of Bolzano, TU Delft, and Eindhoven. This is the site of the project, so if you want to check more detailed information, you can go on this site. I think it will remain after the presentation we can share on LinkedIn maybe. And today I will speak about the VP1, so that is the design of the smart mobile factories and logistic. And then I will have some hypotheses for the VP2 and VP3 with some specific ideas. The first VP was related to the design of smart mobile factories. So we had to understand the requirements of this factory. And so we started to collect information with the EuroTube. And at the end of these meetings, we had a summary of the main and subordinate requirements for the smart mobile factories. For example, one of the main requirements was to allow easy assembly and disassembly of the factory, obviously. allow the adjustment of the factory, so we can change shape and dimension and volume of this factory. We have to reduce the carbon footprint for the factory. So the idea is not to have a concentrated and static position for the production of the rings of the Hyperloop, but we move the factory nearby the head of our building site and construction site to reduce the movement of all the pieces. And then we have to minimize the logistic and the interlogistic effort in the factory and of the factory. So after this requirement, we look at the analysis of the volume and the working areas that we need. And the idea is that we can use for the foundation of the factory a so-called foundation called tatami. That is an ancient idea of the Japan culture, in which with a unique model for the foundation, we can realize different dimension and shape of the working areas. So we can changing by the site in which we want to build the factory, we can have different volume, different form of the factory without losing in usability of the factories. Then we move on with the idea that we can divide the factory. So we have model 1 that is specific for the prefabrication of the component. Then we have a drying area, and then an assembly factory for the assembly of the component, the post-tensioning, and the sealing of the finished tube that we know that is composed by 10 unique pieces of ring made in concrete. And then these 10 pieces has to be post-tensioned, and then we have to create the vacuum inside with the procedure of the sealing of this tube. The idea to split the factory in two when it's possible, depending on the site we want to build it, is that we can move the first part in advance and keeping on the old location with the assembly part, so we can finish all the components that we created. Meanwhile, with a new location, we can start in the prefabrication again, and the casting and the curing of the new pieces. And then when in the old location we finished all the pieces, we can move the second part in the new location, and we will find some pieces already made to make the assembly part again. So we have the hypothesis of to have a unique factory that is in continuum, and then there is the idea to have two different pieces of factories that can work independently by one to the other, in which in this idea we can have a continuum production and continuum working area without losing any time for the relocation of the factories and rebuilding the factories. So then we have three hypotheses of material to create these mobile factories. The first one is made in concrete, that is made in a prefabricated wall of concrete. The second option is made by wood, that is made from crosslam and lamellar woods. And then the third one that is composed by a pneumatic structure that we can use a lot of time, and it's very easy to move in a new location and rebuild. Now I can show you a brief video of these three different options. This is the option with the pneumatic solution. You can see that we divided the factories in two different working areas. The first one on the left is the curing and construction and creation of the unique ring. And in this second, we have the part in which we built the final tube with the 10 pieces, and then we make the sealing and pretensioning activities. Now we can move on the second type of factory that is made in wood. That is a good option, but we have the problem that the element in wood we cannot reuse so many times like the pneumatic one, because we have problem with the connection between the structure wood to wood and wood with connection, so wood to concrete. And this is the third one, that is the most unfriendly, speaking about the environmental sector, because we have to move very heaviest component for the factory that are made in concrete. So using this BIM model, I can extract the build of quantities with all the components for the 3 different versions of the factory, and using this data to have also a life cycle assessment analysis to understand which is the most friendly for the environment and the most useful, so for more time useful type of factories. Then I created the VBS, so is the work breakdown structure of all the activities that we have to do for the construction of this factory. So in the first column, you will see the site layout setup with all the tasks. Then we have a prefabricated construction for the foundation and assembly in the site. And then we have the 3 different options, that is the wood one, the concrete, and the pneumatic one. And we can see that the pneumatic one is the most easy to assemble, and it costs less in terms of environmental cost, using less also machinery. So we have some machinery that we have to use that for the preparation of the layout and the site and the assembly of the foundation. So we cannot change this part of environmental cost. But if we can choose which is the less complex to build, obviously we can move on the pneumatic one, because we need some truck with a crane to move the pieces of the container, and then with another with only a compressor we can build the factory. We can also study different layout of the factory. In this case, it's called the layout T. So the factory is a unique, so it's a unique pieces with the drying area above, and the strength that you have one single structure, so you will have less construction effort, but we have several shortcomings. For example, the higher transportation effort. Mixer trucks have to go inside the factory, so we have air pollution, more noise, and it's not possible to split the module A and the module D to work independently. Then we have the layout L, in which we have the factory split in 2 modules, and the strength that we have more flexibility of the working spaces, less transportation effort, and the module A and B can work independently. We have indeed some shortcomings. So the module 1 and module 2 are divided, more time to build. We have difficulty of FIFO, that is the acronym of first in and first out of the component for the storage area. And the mixer truck also in this case have to go inside the factories. Then we have the S solution, that is the most interesting to build if we have enough space in the construction site, in which we have more flexibility, less transportation effort, and again, the module A and module B can work independently. The shortcomings are similar on the L solution, but we can see on in the table in which make a comparison, we have less effort for the movement of the component, because we can move directly, maybe using some railways inside the factories, the component in the drying area, and again is more easy to introduction in the sealing part and assembly part of the factories. Each component and each asset, every asset of this BIM model are modeled unique, and I created a specific library with some attributes that we can use when we want to extract and use the model in the Unity environment. So going through and versus the digital twin environment, in which we can add physics and real movement and real sensor to the model, because the BIM is a sort of static photo of the working areas and the task and the movement of the machinery inside the factory. With the digital twin, we can have real-time data that come from the real factories in the future, and we come back with the real data that we can use also in the digital model of the factories. We can divide the digital twin in two. So we have a system monitoring of the building scale with also external data. That is maybe the monitoring of the working and the construction site of the factories, the scheduling of the construction activities, so the shape, the space that we need for each task and working areas, and the optimization of the condition of the internal part of the factories. And also have data, in real-time data, of the logistic and with the management of the storage logistic and component movement. And then we can have another type of digital twin that is on machinery scale, in which we can focus maybe on the mixing concrete area with the temperature and mixer data, so we can have real-time data of the concrete that we will create the unique ring. We have also the possibility to look after the alignment phase or the pipe sealing phase, in which we have also to control maybe if we have reached the vacuum inside the final pipe of 20-meter pipe. This is an idea of digital twin. So I using maybe VR or AR asset like I don't know, HoloLens or Oculus. We can have a look inside the factories and have some dashboard to have real-time data on how our machine or working area are really working, and if we have the correct condition internal of the factories, or maybe some danger that coming for the worker inside the factories. And I created a first hypothesis of moving inside the digital twin of the factory. This is my avatar I called Gustav, that can work inside the factories, look after some information and move some component. And this is an environment in Unity, and I started making some coding to make some tests of the digital twin of the factories. Then I move also in the GIS environment, in which I tried to locate the factories in a real environment. So this is, you can see the location of the factory is an hypothesis of track between Zurich and Bern. And we find some location in which we can really build the factories. And we make some tests also in a 3D environment in which we can place the working area of the factory nearby the pipes that pass by the city. Now, for finishing my presentation, I can have a final focus on also in the wood hypothesis that is very interesting for the South Tyrol, because South Tyrol is well known for the wood industries. So we tried to improve the biggest problem of the wood factory, that is not the material, because wood is very friendly for the environment, but we have to focus on the connection. That is the part that we cannot reuse so many times as we want. So with a bachelor thesis that I follow as a tutor, we collected information on these specific nodes, that is wood connection between wood and wood, and the connection between wood structure to the foundation that is made in concrete. So we make an hypothesis to have 3 different connections with the concrete, and we decided for some characterization in which we can make some vote and some comparison between structural seal, production cost, durability, versatility, assembly time, number of reusable time, and environmental sustainability. The same we created for the connection wood to wood, with also in this case some vote that we gave with the local company. And so we decided the final solution that make more reusable also the wood structure. So we can reduce the difference of the life cycle assessment between the pneumatic one and the wood hypothesis of the smart mobile factories. I would like to finish my presentation with I can make underline some publication that we have during these 2 days, the 2 years of project. And if you're interested, you can take a look maybe on is open, so you can see the publication maybe on Scopus or other site. So thank you for the attention, and I'm here for questions.
Thank you, Andrea. It is very interesting, at least for me, from my side. So I thank you for your presentation too. And I have just seen a couple of questions in the Q&A that I might address now, since we also have time. So the first one is about in the Hyperloop landscape, we see that there are many organizations designing with steel, not concrete. For example, like Eurotube. So how do you imagine those type of smart mobile factories not for concrete tubes, but for steel tubes? Do you have any plan B for steel tubes?
I think that the idea to have a reusable shape of the factories can obviously change if we need more spaces or less spaces, because you can see with the tatami, maybe with the steel construction, we don't need some working area like, I don't know, the curing part of the pipe. So we don't need so much space, and we can reduce the entire factories with less component and less foundation pieces, and also the dimension in the highness of the factories maybe needs less space, so we can reduce using the pneumatic tent very easy. Instead of concrete, we can also use in the steel production or other type of production, because maybe we can build railways, we can build a bridge, I don't know, we can reuse these factories for every infrastructure project, in my opinion. So is the idea of mobile factories that is not connected only with the production of Eurotube. Obviously, these are use cases, but we can use the factories anytime and with any other production of infrastructure.
Good, good. Then it is very good to hear that it is not limited to only concrete use cases. Yeah. Wonderful. So the next one, this concept, the smart mobile factory, would be very interesting for either potential companies, private companies, or even for state governments.
For sure.
Because they might use actually this concept for tenders, for example, in Hyperloop projects. So do you have any plans to let them to use your concept? For example, do you have any commercial purposes afterwards, after your PhD? Do you have...
Maybe the most interesting idea is to work on the tatami and to understand how we can create the pneumatic tent using a recycled component of plastic or other stuff. So we can also be more friendly with the environment and have a better life cycle assessment, because the cost also I see that is connected also Sam, that is a colleague of mine that is working on the project. The most important impact of the mobile factory at the moment are the foundation. So maybe we can think about to improve this specific part to reduce the environmental cost. So we'll see.
Good. We are looking forward then. There's one more question too. You have some type of layout types like S, for example. So this layout types is really depending on the surface area available for the field lab.
Yeah, at the moment that I'm here to work in Zurich to have the real construction site that is nearby in Düsseldorf, and the idea is to use again the possibility to make a different shape with the tatami approach and the pneumatic one to make the real size, real shape for the case of the field tunnel. So this is a general approach for the S or L or T shape, but maybe for the field time will be the field lab shape. So we will work on this next week.
Okay, and then how will you make sure actually you again choose the best layout type
In this case, we don't have to choose the best layout, but
for future
we
ones.
have to make an adaptation of the optimum to the real construction site. So this is the site, the shape, if we have enough space to build in this form. But the field lab has a very restricted constraint because we are in an airport and we have a real building nearby. So we have to maybe have a shape that is not so convenient, but is useful for that case. So maybe will be not so optimized, but we have no choices in that case. So we'll see.
Good, very good. So thank you very much for your
Thank you.
presentation.
Yeah.
And I think we can continue with Luka Ekart. Hi, Luka.
Hi there.
Luka is, he has defended his master thesis in structural engineering design, structural engineering from TU Delft in the Netherlands. And today he will present his thesis to us. So
Yes.
You can
Right.
continue.
Let me share the screen.
Sure.
Okay. Can you see it?
Yes, we can see it.
Okay, perfect. Okay, well, thank you for this short introduction. My name is Luka Ekart. I've recently graduated from TU Delft from structural engineering with a specialization in steel structures. And I've done my thesis at Ivy Group company with the title Investigation of Hyperloop Skeleton Tube Design. Here is the content of today's presentation. First, I'll briefly talk about the benchmark design, the plane tube design, which is currently used at European Hyperloop Center in Groningen, Netherlands. Then I'll introduce to you the skeleton tube design, as well as the results of it. Furthermore, I'll talk about detail engineering for the skeleton tube design. And after that, I'll showcase the comparison study between the plane tube design, the benchmark design, and the skeleton tube design. And I will end this presentation with conclusions. Okay, so first of all, the benchmark design has been taken the already existing design, which is located at European Hyperloop Center. It has been designed by Hard Hyperloop, and I've named it the plane tube design, which is, it's just a simply spirally welded design. I had the opportunity to visit the production site as well as the test site in Groningen. The global dimensions of the test site are as follows. The total length is 420 meters. A single tube segment measures 16 meters in length. It has a diameter of 2.5 meters, and the thickness of the tube is 16 millimeters. Now, going through the figures on the bottom on the left-hand side, this is a picture taken at Mercon production site. Those are already assembled tube segments. Then a bird's eye view of the test site, and on the right-hand side, you can see an expansion joint, which accommodates thermal expansion and contraction. On the left-hand side, you can also see the inner components. Starting from the top, we have the levitation rails, then there's a propulsion rig, guidance rails, and the last rails, I named them safety rails. So in case of an energy loss, the pod can simply drop on top of them. Now, this is a design by Hard Hyperloop, which has been validated and analyzed, and it serves as a benchmark design in this research. Now, what are the infrastructure concerns? Some of them are such as passenger safety, financing, government regulations, public acceptance, maintenance costs, and also due to potential length of the Hyperloop infrastructure, there's a big factor of environmental impact. And due to that, many engineering firms are continuously researching and developing lightweight lightweight Hyperloop tube designs. Now, some of them are presented on this slide. All of them were promoted by Tata Steel already back in 2018. Now, they can either be single layered, as seen on the left-hand side, or double layered on the right-hand side. And although they might differ in their cross sections, they have one thing in common, which is that all of them are lightweight. And another such design is the skeleton tube design, as seen, which was the focus of this thesis. The global dimensions of a single tube segment are the same as of the benchmark design, of the plane tube design, where the length is 16 meters and the diameter is 2.5 meters. Now I'm going to run an animation just to showcase how the tube is constructed. So a single tube segment has 16 rings, which are spaced by 1 meter center to center. There we can see 18 stringers, which are the longitudinal members, and consequently also 18 plates. Those components will also be now seen on the right-hand side. So I talked about the stringers and the rings, as well as the plates. Furthermore, we can see flanges, which mark the beginning and the end of each tube segment. And then we see rail supports onto which the rails are being attached to, and then the shims. Now the shims are attached to the flanges. They're fully fixed, and they have two purposes. One is to support the stringers in those slotted holes, as it can be seen here. And then they also have like a saddle onto which the plate is transversely connected. Now, the skeleton tube design has been showcased by Tata Steel for the first time in July 2022 in one of their promotional videos. And then furthermore, it was presented during the European Hyperloop Center kickoff event. You can also see two models, the plane tube design and the skeleton tube design, one next to the other. Now, what does it remind us of? It can remind us of an aircraft's fuselage structure or a submarine structure. And in both cases, we can see the rings, the stringers which connect the rings among each other, and then the shell which forms the shape. Now, before I'll present to you the FEM results, and before I could make a global model, I had to model rail supports. I started out by identifying the location of the inner components. Then the first iteration of the rail supports was just a ring reinforcement. And based on the location of the inner components, I've designed the rest of the rail supports. At this stage in the analysis, the model exhibited a plastic response at those two locations. This is because of a sudden change in stiffness of the ring, and therefore the stress surpassed the yield strength. Therefore, I've extended the edges of the rail support, and this did not only mitigate those stress concentrations, but it also additionally reinforced the structure. So in this research, I've made two assembly models, the full-scale model, the 16 meters long model, which was to verify the global vertical deflection, and then a shorter model, which had more details, a 5 meters long model for the ULS verification, as well as for the buckling analysis. Now I'll go through the load cases which are considered in this research. First of all, it's the self-weight, which is self-explanatory. Then we have the vacuum pressure, which is acting on the on the plates, on the inner surface of the plates. Now, the vacuum pressure is uniformly acting on the inner surface, and moreover, it's acting normal to the surface, looking at the figure on the bottom. Furthermore, the snow load was added on the top of the tube, the wind load acting from the side, and then we have the rails load and the static pod load, which was assigned at the locations where the rails were supposed to be attached, those red surfaces. In this research, I've considered 10 load combinations. In this presentation, I'll present 3 of those, the LC1, LC2, and LC10. Now, LC1 only considers the vacuum pressure as the critical load case. In LC2, the snow load is added on top of it, and the critical load combination, LC10, considers all of the load cases, which I've just presented. So let me continue with results. First, I've verified the global vertical deflection. The SLS load combination was used for this analysis. Now, there are 2 deflection limits. The first one is imposed by the Eurocodes, which is 3.5 millimeters. And the second one is imposed by the levitation rails. Now, the levitation rails are made out of 1 meter long segments, as seen on the bottom figure. And there is a 1.5 millimeters allowed vertical misalignment for the rails to be operational. So this is a second deflection limit. And upon analyzing the assembly, the global vertical deflection resulted in 3.34 millimeters. Now you can see that I've taken the data from the side of the ring. This is because a vertical ovalization is expected in the rings of the structure of the assembly. But when you take the data from the side of the ring, those results are unaffected by vertical ovalization. And to add, based on the global vertical deflection, the deflection is satisfactory. Then I'll present to you the local deformation of components. Now, in this graph, you can see deformation of critical plate, stringer, and ring. Now, 3 load combinations are presented in this one graph. And those load combinations are also marked with the time steps, as seen over here. Now I'll run an animation just to showcase how the deformation is being, how the deformation propagates during the load combination 1. So on the top right, you can see the development. And we can see that the largest deformation exhibits in the plates. Now to also showcase the deformation of the frame, I've removed the plates. Now this deformation is scaled up just for visualization. On the bottom, you can see that the frame gets squeezed together. So the largest deformation can be seen at the side of the tube. Now this can be justified by looking at the stiffness of the rings. Now, when I modeled the rail supports are fully fixed onto the rings, meaning that the stiffness of the rings is severely increased on the top side, while the bottom side of the ring has a decreased stiffness. At 2 locations, we can also expect a hinge-like behavior, because this is where the stiffness suddenly changes. Now I'll run an animation of a single ring deformation. Once again, it's scaled up just for visualization. The wireframe will also represent an undeformed shape. So what we see is that the sides of the ring gets compressed together. Furthermore, see two hinge-like behaviors, as stated before. What else can be concluded from here is that we can define the major axis or the strong axis of the ring and the weak axis of the ring. Next, I'm going to talk about the plate deformation. So upon closer investigation, I've noticed that the plate did not uniformly deform, but there was a larger deformation at the sides of it, while, yeah, the middle had a smaller deformation. So this can be explained by by taking a single strip from the plate, which is positioned between the rings. I've taken the cross section of it and scaled up the deformation, and you can clearly see a sinusoidal-like deformation. Now, this can be justified by deconstructing the forces within the plate. So if we deconstruct the force at the side of the plate and looking at it from the global coordinate system, it dissolves into a horizontal force component and vertical force component. While in the center of the plate, there's only a vertical force component. Now, due to the horizontal components, the center of the plate is tensioned, and consequently, the deformation is lessened. Next, I'm going to talk about is the strength verification. Now, this graph can be read in the same way as the previous one with deformation, but in this case, on the y-axis, we can see stress. I'll run the animation of the stress development within the assembly on the right-hand side due to load combination 1. Now we can see that the stress concentrations are visible at the locations in the ring where the rail support ends. This was as expected. And the largest stress was 342 megapascals, which is which is below the yield strength of 355 megapascals. Now, upon further investigation, I've noticed more stress concentrations. So in the top figure, you can see the one which was visible in the animation, and then on the bottom figure, there are stress concentrations at each and every string-to-ringer connection. And this is also where the stress reaches 342 megapascals. Next, I'm going to present to you the eigenvalue buckling analysis. So to understand the load path due to the critical load case, which is the vacuum pressure, the vacuum pressure, the force is transferred through the plates onto the stringers, and then through the stringers onto the ring. So the ring is the component which is in full compression, and it was also expected that the buckling will happen within the ring. And when I ran the analysis, the buckling did exhibit in the webs of the ring, as it can be seen in the figures here and there. And for this verification, for this analysis, I've used a full nonlinear analysis approach based on DNV standards, and it has the following workflow. First, I ran a linear buckling analysis. And then I've chosen the buckled shape that I wanted to investigate. I've determined the imperfection scaling factor, which was also done based on DNV standards. And then I ran a full nonlinear post-buckling analysis. Now I'll run the animation of the buckling failure. If we focus on the central ring, we can see that at a certain point, it will simply buckle inwards. And at this stage, at this point, this is a collapse of the structure. I've investigated this buckled location from up close. So we can see that the webs of the ring buckled outwards, while the flange of the ring buckled inward. Looking at the von Mises stress, the maximum stress before the failure was 359 megapascals. and seen in this figure. And in the graph, you can see that there was a linear increase in stress up to a vacuum pressure of 0.084 megapascals, which is 84% of the intended vacuum pressure within the tube. Then there's some amount of strain hardening until the failure at the pressure of 0.17 megapascals. So to be on the safe side, we could say that the buckling factor for this design is 2. Next, I'm going to talk about is the detail engineering. So the critical connection, well, the critical locations in this assembly are the ring-to-stringer connections. And there are 18 of such connections per ring. And considering that there are 16 rings per tube segment, this results in 288 critical points in the model. And yeah, that means that this detail needs to be analyzed and investigated. And I came up with the following connection design. So it's a bolted steel bracket connection design, which connects the ring and the stringer. Now this detail is primarily in compression, and what else is special about it is that the bolts are non-preloaded. This is because of the slenderness of components, and I wanted to avoid any preliminary deformations or deformations during the assembly due to preloading of the bolts. Now, let me take you through some of the specifics of this connection. The first one is the slotted hole. Now, the load path goes through the stringer, is transferred from the stringer through the webs of the stringer onto the ring. Now, the stringer will deform outwards as well as downwards. And if the slotted holes would not be present, there would be a threat of the bolts simply shearing through the webs of the stringer. So this accommodates any vertical movement. The second specific is the curved surface of the connector. It follows the same radius as the radius of the ring. And this reassures that the force is evenly distributed from the stringer onto the ring. And this also mitigates the stress concentrations. So then I made a local model and analyzed it also in ANSYS software. Going through the stresses, we see that in the bracket, the maximum stress was 326 megapascals, but this was a stress singularity seen over here. But what it's important is the stress at the location where the force is being transferred through, and it's roughly 260 megapascals. But what's important is the stress in the ring, which resulted in 226 megapascals. Now, comparing this value with the previous value, which was 342 megapascals, we can see a severe reduction or decrease in the stress, meaning that, yeah, the design serves the purpose of reducing the stress concentration and mitigating the plastic response. Lastly, I'll talk about the comparison study. Now, I'm slightly time limited, so I won't present to you the FEM results of the plane tube design, but I will only go through the comparison study. First is the weight comparison. Now, I compared both designs in terms of total weight. In the first comparison, I did not include the rail supports, meaning that the tube would only serve a purpose of retaining vacuum pressure, but not supporting the rails and the pod. And in this case, the weight efficiency was almost 38% in favor of the skeleton tube design. And in the second comparison, I've added the rail support to both designs, and the weight efficiency decreased down to 28%. But this is still a very significant weight reduction. Now I'll go through the comparison of the other aspects of both designs. So I've evaluated the performance of each design and with using the following scale, which can be seen on the left-hand side, going from excellent to bad. Now, in terms of ULS, SLS, and impact load, the plane tube design quite significantly outperforms the skeleton tube design. This is due to a much thicker, much thicker skin of the tube. When it comes to the stability aspect, now this cannot be fully compared because the plane tube design only exhibited global buckling, while the skeleton tube design only exhibited local buckling. But in both cases, it was satisfactory. When it comes to the sustainability, as previously showed in the tables, the skeleton tube design outperforms the plane tube design. And lastly, in terms of production and maintenance, now the plane tube design is it's a very simple design. It's just a spirally welded tube, while the skeleton tube design is constructed, well, it's made out of 6 different components, and each component needs to be individually fabricated, and this can have quite an impact on the production phase as well as the maintenance, because many local failures are expected. Okay, let me go through conclusions of this research. The first one, the ULS is conditionally satisfactory. Now, why I've decided to phrase it like that is because a nonlinear response was initiated at the connections between the ring and the stringer, but the assembly nonetheless exhibits an elastic response. Consequently, there is also the design also has an insufficient capacity to bear any additional loads, meaning that if there would be any additional loads, we could expect a full nonlinear response or a fully plastic response. I've identified 2 stress concentrations in the assembly at the ring to stringer connection, as well as at in the ring where the rail support ends. The global vertical deflection was satisfactory based on the deflection limits. Local deformations were also within the limits. This is primarily meant for the plates. Now, due to the very slender design and very small thickness of the plates, the design does not offer any resistance to accidental or impact loads. So this is one of the major drawbacks of this design. And lastly, the steel bracket design reduced the maximum stress in the assembly from 342 megapascals down to 226 megapascals. And with that, I reassured that the assembly did exhibit an elastic response. And with that, I would like to conclude my presentation. Thank you for your attention. And now I'm open to any questions that you might have.
Thank you very much. And of course, we have some questions to you too. First of all, the first question is from my side. Can we reach your thesis somewhere? Is it publicly available? If yes, where can we find it?
Yes, it is available on the TU Delft repository. So if you just Google my title of my thesis, you will find it. It's going to be the first search finding.
Okay, now I can continue with the questions from the audience. So what are the potential applications of the skeleton tube design outside of Hyperloop context? And what unique characteristics make it suitable for these applications?
could you, excuse me, could you repeat the question?
What would be the potential applications of this tube design outside
Mhm.
the Hyperloop applications?
So potential applications of this tube design within the Hyperloop.
Outside Hyperloop.
Oh, outside. Oh, yeah,
Outside.
that's an interesting question because what has been proven is that this design can retain vacuum pressure without a problem. The problem appears once additional loads has been assigned to it, as well as in case of any accidental or impact loads, meaning that the shell would get instantly penetrated. So in terms of other applications, yeah, if there would be a need of a space which should be under vacuum pressure, and this environment would be controlled, meaning that there would be no accidental or environmental loads acting on it, then this design could be used to create and retain vacuum pressure. This is one of the potential applications.
Good, very good. The other question is, what would be the advantages and disadvantages of this design? But I think you perfectly answered in your comparison table.
Mhm.
So for the sake of the time, I can skip this question.
I can go back to the
Yes, I mean, if you want to summarize very briefly.
yes, to summarize very briefly, I can say that there is a big benefit in terms of sustainability, but the major drawback is that it's very susceptible to any kind of penetration, to any kind of impact load. And furthermore, I've only ran a static structural analysis. So there should be analysis performed on based going through the dynamic loads, assigning dynamic loads on this structure, as well as fatigue, and the list goes on which other factors should be considered for the Hyperloop application. So it might look very promising from my research, but this is just the first phase. And it could prove that there are many other drawbacks as we consider other aspects in the Hyperloop application, such as the moving pod, and it could be that this skeleton tube design does not perform that well to any dynamic loads, for instance. So yeah.
Okay, very good. And I will take one more question for the sake of time. About the connection between curved rib and rectangular shape beam. Have you thought about the cost? Cost-wise, it looks like an expensive piece to manufacture. Have you looked into it?
So there, in the paper, you can also find where I mentioned where I stated what kind of production processes, fabrication processes could be utilized for this connection design. Now, one of them is obviously a CNC milling, but this is a very expensive process because there would be a lot of material waste. The second one is to simply mold those brackets, but there is a drawback that with molded steel, if you mold those brackets, there might be a very brittle failure modes. And the last production process could be just to weld those plates together. So looking at the design, we can simplify it into 3 parts. The side plates, which are 2 of them, identical, and the middle plate. So each one of them could be produced separately and then just welded together. And this could potentially be the most cost-efficient production process. But this is something to be further investigated.
Okay, very good. So thank you very much for your presentation.
No worries. Thank you
It
for
was
this
very
opportunity.
joyful for us as well. So,
Yes,
before
I will stop
closing,
sharing.
yes,
Yes,
please.
in a second.
Yes, and before closing the session, I would like to remind you, everybody, that we are gonna have our next edition next week, next Monday at 6 p.m. again at the same slot. And next week, Sasha Lem from the European Hyperloop Center will be with us, and Alexei Vasily from Hochschule Emden will be us, and they will be talking about their, of course, Sasha is about Hyperloop Center, and Alexei is about her thesis. So I hope to see you next week, everybody. And I wish you a happy, nice evening.